Welcome back to the deep dive. Today, we're stepping back in time, all the way to 1959, to examine a patent for a helicopter drone, a drone that was truly ahead of its time. We're looking at Edward G. Vanderlip's 1962 patent for an omnidirectional vertical lift helicopter drone. Now, our listeners already know the basics of drones, so we're going to dive deep into the technical details that make this patent so fascinating.
It's remarkable how Vanderlip tackled the fundamental challenges of drone flight. Even with the technology available in his time, he envisioned a drone with 4 rotors, a quadcopter design as we know it today, but with some very innovative twists.
One of the things that jumps out right away is how he addressed the issue of torque. Conventional helicopters, they need a tail rotor to counteract the torque from the main rotor. But Vanderlip, he found a way around that?
He did. He designed the rotors to be arranged in pairs, on opposite ends of horizontal axes, and those pairs cross at right angles. And the rotors on each axis rotate in the same direction, while the pairs on opposite axes rotate in opposite directions. This counter-rotation means the torque forces cancel each other out. No need for a tail rotor.
So he simplified the design and made it inherently more stable. Now, how about how this drone actually moves? The patent details a system where tilting the axes of those rotor pairs controls direction. And get this, the drone doesn't have to change its orientation at all.
That's a key point. The drone can move sideways, backwards, even diagonally,
Yeah.
all while keeping its nose pointed in a single direction. This is done through a combination of tilting the rotor axis and adjusting what's called the collective pitch of the rotors.
Collective pitch. Could you explain that for our listeners?
Collective pitch means changing the angle of all the blades on a rotor, all at the same time. So instead of relying on what's called cyclic pitch control, where the angle of each blade changes as it spins, Vanderlip used collective pitch adjustments for each rotor and each pair.
Interesting.
By making subtle changes to the collective pitch of the rotors, he achieved roll, pitch, and yaw stability. It's like fine-tuning the thrust, coming from each rotor, to keep the drone perfectly balanced and under control.
And the patent goes into detail about maintaining a level platform, especially important if you want to carry sensitive instruments or cameras. And this is 1959, long before GPS and advanced flight controllers.
Right, to achieve that level platform and keep a constant orientation. Vanderlip integrated vertical gyroscopes and accelerometers. These would detect any tilting, and the control system would then make adjustments to the rotors. To counteract it, he also included a compass to maintain the drone's heading, its direction, even without visual cues.
So this drone was already thinking about maintaining a steady heading and a level platform, crucial for applications like aerial photography or surveillance. Now let's talk about controlling the drone. How do you actually fly this thing?
The patent describes a system that blends remote control with onboard automation. The drone would receive radio commands for altitude and lateral movement, that's side-to-side movement.
Okay, so there's remote control,
Yeah.
but also these onboard instruments,
Yeah.
contributing to the drone's ability to fly autonomously.
Yes, he incorporated things like barometers, radio altimeters, even Doppler systems to measure altitude and maintain stability. These instruments would work with the remote control commands, ensuring a steady hover, even if the signal was interrupted.
I find the concept of mixing circuits particularly interesting. These circuits blend pilot commands with the onboard stabilization, allowing for smooth transitions between manual and automated control.
A remarkably forward-thinking concept for the time. It suggests that Vanderlip envisioned a system where the pilot could switch between direct control and letting the onboard systems handle tasks, like maintaining altitude.
Like we see in modern drones, where you have levels of autonomy and pilot assist. But Vanderlip was already considering this back in 1959. Pretty amazing. Now let's talk about the collapsible design.
Sure. The patent explains how 2 of the drone's 4 pylons, those are the structures that support the rotors, can be folded inward. This makes the drone much more compact for storage, especially on a ship.
So you fold those 2 pylons in and stow the drone away neatly below deck. A very practical design. He was thinking about the whole life cycle of the drone, not just the flight itself.
Absolutely. He even details hinges on the rotor support tubes and detachable connections for the drive shafts to make the folding mechanism possible. And he emphasizes proper alignment when unfolding, so the rotors don't interfere with each other.
Clearly a lot of thought into making this a functional design. Even the details of storage and transport. We need to look at the illustrations to really understand this patent.
I agree. Figure 1 shows the overall design, those 4 rotors and the pylons. Figure 2 shows the drive mechanism, ensuring opposite rotation of those rotor pairs. And Figure 5 shows the collapsible design, how those 2 pylons fold inward.
The illustrations really help. Now, in the next part of our deep dive, we'll continue exploring the patent and looking at the specifics of the power plant and drive mechanism. Stay with us.
Let's talk about how Vanderlip tackled a very important challenge. For any drone that's meant to carry instruments or cameras, maintaining a level platform, any tilt or wobble could really throw off the data, especially back in 1959 when stabilization technology was pretty basic.
The patent really highlights gyroscopes and accelerometers as being key to that level platform. Can you walk us through how these sensors were incorporated into the drone's control system?
Think of a spinning top. It resists any attempts to change its orientation. A gyroscope works in a similar way. It senses rotation around a specific axis. In Vanderlip's design, these gyroscopes, they would have detected any tilting, any angular motion of the drone's fuselage.
So let's say the drone tilts forward. The gyroscope would sense that and send a signal to the control system.
That's right. The control system then takes that information and adjusts the rotor speeds or the tilt angles to counteract the tilt, bringing the drone back to level.
And the accelerometers. Those work together with the gyroscopes to make sure everything stays stable.
Absolutely. Accelerometers measure linear acceleration, which includes the acceleration due to gravity, so the control system can tell if the drone is tilting or accelerating in any direction.
So if the drone started to accelerate forward, the accelerometer would pick that up, and the control system would adjust to maintain a stable hover. He really thought of everything when it comes to stability.
He did. He also included a compass to make sure the drone could keep a consistent orientation, even without any visual cues. This would have been really important for missions beyond the operator's line of sight or in environments with limited visibility.
Like giving the drone a sense of direction, making sure it stayed on course, even if it was flying over a vast empty ocean or a featureless desert.
Exactly. The compass acted as a reference point for the drone's control system, enabling it to navigate on its own and carry out missions reliably. Vanderlip really envisioned a highly automated system. The patent says the drone could maintain a stable hover and even follow pre-programmed flight paths without any constant input from the operator.
So even back then, he was thinking about automating certain aspects of drone flight. That's really ahead of its time.
He understood that automation would simplify drone operation and make it useful in more situations by using onboard sensors, feedback loops, and control logic. He gave the drone a degree of autonomy. It could make adjustments on its own to stay stable and on course.
And to make sure that manual control inputs
From the operator
would work with the automated functions. He came up with the idea of mixing circuits.
Yeah.
These circuits were really important for smooth and predictable flight.
Mixing circuits were essentially electronic circuits that combined signals from various sources, like the remote control and the onboard sensors. By blending these signals, it created a single control signal for the motors.
So these circuits were like a central hub, making sure the drone responded smoothly to both the pilot's commands and the automatic adjustments from the stabilization system.
That's right. These mixing circuits prevented sudden jerks and unpredictable movements, ensuring a smooth and coordinated response, no matter what was controlling it.
This concept is still relevant today. Modern drones need to blend manual and automated control.
Absolutely. The fundamental principles haven't changed, but the way we implement these mixing circuits today is far more sophisticated, thanks to advancements in electronics and computing power.
Let's move on to what really sets Vanderlip's drone apart: its ability to fly in any direction, without needing to change its heading. The patent calls this omni-directional flight. This was a revolutionary concept.
It was. This was way before drones with GPS and advanced flight control were common. Vanderlip achieved omni-directional flight through the drone's symmetrical design and those tilting rotor axes. Instead of turning the whole drone to face the direction it wants to go, like a traditional helicopter, this drone could just tilt its rotor axes to create thrust in any direction.
The drone could fly sideways, backwards, or diagonally, while keeping its nose pointed in one direction, almost like magic.
It was a fascinating concept with a lot of advantages, especially for things like aerial photography and surveillance.
Maintaining a constant heading while moving in any direction would be perfect for getting stable aerial footage.
Exactly. Imagine trying to film something with a normal helicopter. It has to constantly adjust its heading to change direction. The camera would be moving all over the place. But Vanderlip's drone could keep the camera perfectly steady on the target, no matter how the drone was moving.
Like having a tripod in the sky.
Exactly. And for surveillance, this omnidirectional flight would allow the drone to watch a target from a distance. It could circle or move around the area while staying pointed in one direction, making it harder to spot.
So it's not just about nice pictures, it's also about positioning and stealth.
Right. Vanderlip was ahead of his time in seeing the value of separating the drone's movement from its heading.
And to make it easier to store and transport, a drone with 4 big pylons. Vanderlip came up with a collapsible design, another example of his forward thinking.
He knew that a large drone could be difficult to manage, especially when space is limited.
The patent says that 2 of the 4 pylons, the parts that hold the rotors, can be folded inward, making the drone much smaller.
He included hinges on the rotor support tubes and detachable connections for the drive shafts to allow for this folding. Picture the pylons sticking out like the arms of a plus sign. The mechanism would let 2 of the pylons, the ones on opposite sides, fold inward, turning that plus sign into a vertical line.
So instead of a wide footprint, with all 4 pylons out, you could fold it into a much narrower shape for storage. A simple but clever solution.
It is. This would be especially helpful for naval applications, where space on deck is limited. The folded drone could be stored below deck, saving valuable space.
Figure 5 in the patent shows how neatly those pylons fold in. Did he say anything specific about the folding and unfolding process?
Yes. Vanderlip stressed the importance of aligning the rotors when unfolding the drone to make sure the blades don't hit each other when they're spinning. This focus on details shows how practical he was.
It's not just about a cool idea, it's about making sure it works in the real world.
Exactly. He thought about the entire life of the drone, from operation to maintenance and storage.
What applications did he see for this drone? The patent mentions several, from scientific research to commercial use, even military operations.
He saw potential for exploration, surveying hard-to-reach areas, capturing aerial photos, collecting data about the land.
So the drone could be a flying sensor platform, gathering information about places that are dangerous or hard to get to.
That's right. He also saw its potential for military use, especially reconnaissance and surveillance.
It would be great for monitoring enemy positions, gathering intel, and assessing damage after airstrikes.
Its remote operation and autonomy would make it useful in dangerous areas. He also thought it could be used for photography, especially aerial photography. Its stability and maneuverability would allow it to capture beautiful and stable images.
From science to the military to photography, he had a broad vision for this drone.
He did, and it's amazing how many of his ideas are now a reality in the drone industry today.
Vanderlip's patent wasn't just a document, it was a look into the future of drones. And in the next part of our deep dive, we'll talk about how his design could be even better with the technology we have today. Stay tuned. What if we took Vanderlip's drone and reimagined it with modern technology? We've talked about electric propulsion, but what other advances could improve his design?
We could do a lot. One big change would be the control circuits. Those bulky vacuum tubes could be replaced with tiny microprocessors and integrated circuits, much smaller and lighter, but with way more processing power.
It's incredible how much computing power we have in those tiny chips.
Exactly. That would save space and weight. We could have a smaller airframe, maybe carry more payload, or even fly longer. And we could add a modern flight controller. It would take data from the sensors and turn it into precise commands for the motors. The drone would fly much smoother and respond quicker.
So it would be stable and agile.
Yes. And the sensors. Instead of separate gyroscopes, accelerometers, and a compass, we could use a state-of-the-art IMU, an inertial measurement unit. It combines all those sensors into one small package.
A much more integrated system.
Right. And with that data from the IMU and GPS, we could add obstacle avoidance using cameras or LiDAR. The drone could navigate difficult environments on its own and avoid collisions.
Vanderlip's drone used a simple radio control system. How would we upgrade that?
We'd use a much more sophisticated radio system with multiple frequencies, spread spectrum technology, and data encryption, long-range control, reliable data, and more security. The drone could even communicate with ground stations, satellites, or other drones.
Giving it a much better and safer way to communicate. Vanderlip wanted a drone that could fly on its own and be remote controlled. How would we improve that dual control?
Today's drones do both really well. They can follow pre-programmed paths, avoid obstacles, and do complex tasks. But the operator can always take control, a real partnership between human and machine.
Vanderlip was a visionary, but with today's technology, we could make his ideas even better. It's amazing how far we've come since 1959, and it's exciting to think about the future of drones.
It's been great exploring this patent with you and with our listeners. Edward Vanderlip shows us that innovation starts with a spark of creativity, a desire to change things, and a vision for the future.
Thank you for joining us on this deep dive. We hope you enjoyed learning about the roots of this amazing technology. Until next time, keep exploring.